Welcome back, everyone. I am so excited to jump into today's exam prep explainer on real-time software engineering. We're going to dive into a professional university-level masterclass focused entirely on section 21.4 of your text. That is the section on real-time operating systems. Once we've conquered that, we're shifting gears, all right? We'll do a high-energy, rapid-fire master recap of Chapter 21, just to make absolutely sure you are fully primed and ready for those exams. You know, embedded systems, they're kind of the invisible engines running our modern world, and mastering them is an absolutely crucial step in your software engineering journey. So go ahead, grab your notebooks, and let's get into it.
Okay, let's dive into this with a really fundamental question. Think about it for a second. Why don't we just run our real-time embedded systems on the operating systems we use every single day, like Windows or Linux? I mean, it seems like it would be so much easier, right? But the reality is, if you put a standard OS in charge of, say, a car's anti-lock braking system, well, you might literally end up in a ditch. So we really need to understand exactly why these conventional environments fail when they're subjected to strict, unforgiving real-time constraints.
So here's our roadmap for today's masterclass. 1. The need for RTOS. 2. Anatomy of an RTOS. 3. Core scheduling strategies. 4. Key scheduling algorithms. And finally, number 5, our Chapter 21 master recap. Let's move.
Starting with Section 1, the need for RTOS, let's look at exactly why standard operating systems just can't handle these environments.
To answer our earlier question, conventional operating systems like Windows and Linux are, frankly, incredibly bloated. They've got extensive functionality, heavy file systems, background tasks running constantly, and all of that takes up a massive amount of space and significantly slows down program execution. But the biggest issue? They simply do not allow for fine-grained control over process scheduling. In a real-time environment, you absolutely cannot afford to wait for a random background update to finish before deploying a car airbag, right? Now, for very simple systems, we actually bypass the OS entirely. We run on what we call bare metal, meaning the application just provides its own execution support and process management straight onto the hardware. But for complex real-time applications, we have to use a real-time operating system, or RTOS, like VxWorks or RTLinux. These are lean, super efficient platforms designed specifically to offer that fine-grained control, incredibly fast execution, and strictly prioritized scheduling.
Moving on to Section 2. Anatomy of an RTOS. Let's actually look inside the system.
And this brilliantly illustrates how these internal mechanisms interact. You've got the scheduler sitting right at the center, taking in information from the real-time clock and the interrupt handler. It then communicates down to the resource manager, which feeds straight into the dispatcher. It's like a highly coordinated dance, and it's completely designed to guarantee that when a critical event happens out in the real world, the software reacts instantly and predictably. So let's methodically walk through these 5 crucial components. Keep your pens handy because you will definitely need to memorize these for your exam. First up, the real-time clock. This provides the precise timing information necessary to schedule periodic processes. Second, the interrupt handler. This one's vital for managing urgent, aperiodic requests. You know, those unpredictable, irregular events that scream out for immediate attention. Third is the scheduler, which is the absolute brain of the whole operation. It's responsible for looking at all the processes ready to execute and choosing the next one based strictly on priority. Fourth, we have the resource manager. Once a process is chosen, this component steps in to allocate the appropriate memory and CPU resources. And finally, the dispatcher. This is essentially the trigger that actually starts the execution of the chosen processor on the available processor. Working together, they enforce that strict, time-critical behavior.
Which brings us to Section 3, Core Scheduling Strategies. Let's talk about how the processor manages those priorities.
Now, this next concept is absolutely crucial for your exams. The scheduler has to manage entirely different priorities using 2 main strategies. On the one hand, we have non-preemptive scheduling. In this strategy, once a process is scheduled and actually starts executing, it runs all the way to completion, or at least until it gets blocked waiting for an input. I have to warn you, though, this is incredibly dangerous in a real-time setting if a high-priority task gets stuck waiting behind some long-running, low-priority task. On the other hand, we have preemptive scheduling. Here, if a higher-priority process suddenly requires service, say a voltage monitor detects a massive power drop, it can immediately interrupt and pause the executing lower-priority task to essentially steal the CPU. In the strict, high-stakes world of real-time deadlines, preemptive scheduling is very often the lifesaver.
All right, Section 4. Key scheduling algorithms. Let's see how these scheduling strategies actually execute in practice.
Within those overarching strategies, the RTOS uses distinct algorithms. There are 3 specific ones you absolutely must recognize on your exams. First, round-robin scheduling. This is exactly what it sounds like. Everyone gets a turn. Each process is executed in sequence for a set, predetermined amount of time. Second, rate monotonic scheduling. This algorithm dictates that the process with the highest frequency, meaning the shortest period between executions, is automatically given the highest priority. And third, shortest deadline first scheduling. In this algorithm, the scheduler looks at the queue and simply schedules whichever process has the absolute shortest, most immediate deadline next. It's an incredibly logical, straightforward way to ensure the most pressing timing constraints are met first.
And that brings us to Section 5, our Chapter 21 Master Recap. Grab a breath, get ready, and let's zoom out to lock in this knowledge.
First up in our rapid-fire recap is the most fundamental distinction you will be tested on: hard versus soft real-time systems. Remember, time is a literal functional requirement here. In a hard real-time system, missing a deadline is catastrophic. If the system doesn't produce the result exactly on time, it's considered a total system failure. Think of a pacemaker or a flight control system. It's totally unforgiving. But in a soft real-time system, if a deadline is missed, the system's operation is merely degraded, not destroyed. Think of a streaming video buffering on your laptop. I mean, it's annoying for sure, but nobody gets hurt.
Now, what's really interesting here is how we solve a major problem in the stimulus response model. Embedded systems react to stimuli in the environment and produce responses. But what happens if the process producing the data operates at a completely different speed than the process consuming it? Well, we use a circular buffer. The producer process puts data in its tail, and the consumer process extracts it from the head. By implementing synchronization mechanisms to ensure they don't access the exact same slot at the exact same time, this circular buffer brilliantly accommodates those speed mismatches. It minimizes data loss without ever delaying process execution. Next up in the recap, architectural patterns. There are 3 essential patterns commonly used in embedded real-time systems design that you have got to know. First, observe and react. This is typically used in monitoring and alarm systems, where sensors are checked and actions are taken if certain conditions are met. Second, environmental control. This is for systems that manage and regulate physical environments. And third, process pipeline. We use this in data acquisition systems, where data flows through a sequence of transformations, like a raw sensor reading being converted, then processed, and finally displayed.
So, the crucial point we really need to hammer home is this. When you are performing timing analysis on a real-time system, average execution time is just not enough. You must understand the worst-case execution time. Because execution times can vary wildly based on conditional logic or system delays, you must calculate the absolute maximum time a process will ever take to execute. In a hard real-time system, all of your scheduling and priority assumptions must be based on this worst-case scenario. That is how you guarantee, mathematically, that a critical deadline will never, ever be missed.
And with that, we are wrapping up Chapter 21. I want to genuinely congratulate you all on mastering the immense complexities of embedded systems engineering. We've explored everything today, from the unyielding nature of hard real-time constraints, all the way to the elegant fine-grained control provided by a real-time operating system. But as you close your books today, I want to leave you with one final thought. Writing software that works is one thing, but writing software that works within the unforgiving, microscopic fractions of a second demanded by the real world, that is an entirely different discipline. You know the theory now, you know the algorithms, but are you truly ready to strictly enforce the laws of real-time deadlines out there in the wild? Thank you so much for joining me in this explainer. Keep studying hard, and I'll see you next time.